All right, so we've been doing area, and now we're gonna go from that to volume. So let me start this.
Area, when we learned geometry, going over all the formulas for the area of different polygons. Then when we got to calculus, we learned about integration as a new technique for calculating area where curvature is involved. We learned how to take some region between a curve and an axis, or between two curves, and find its area by integration, essentially finding a length and sending it across the region. But in geometry, we also learned about three-dimensional figures, like cubes and prisms and pyramids. We described the volumes of these objects, or the amount of three-dimensional space that they contain, and we had useful formulas to calculate this as well. But once again, when curvature gets involved, all of these formulas are useless. Luckily, just the way we run a line segment across a two-dimensional region to calculate its area, we can run a plane region or cross-section across a three-dimensional region to calculate its volume. This is also integration, just with an extra dimension. Instead of adding up tiny rectangles under a curve.
Okay, so do you remember how here we drew a rectangle like this? Okay, and now the height of the rectangle is the function, right? And then the width is the change in x, right? And so that's one rectangle, and then we did that for every single rectangle and added them up, right? So we're gonna take that same process.
In the limit of infinitely thin rectangles, we are adding up infinitely thin cross sections, which we can call disks. Since each of these disks is a two-dimensional area, taking the integral of an area function will give us volume.
Okay, so basically,
for example, take the sphere.
Okay, so look here.
Each of these disks.
If I can draw a disk here, right? What shape does that disk have? A circle. Okay? And look, it's got a tiny, tiny thickness to it, right? If this is the x-axis, that tiny thickness is the value in x. So now, the area and that times that tiny thickness gives me what? The volume of it, right? So if I've got a disk like this and then a tiny little thickness to it, okay, I can find the area times that, and that's the volume. So if I find the volume of that one, and then if I draw an infinite number of them, I can add them up and I can get the volume of my entire shape. Okay? Are all of the disks going to be the same size? No. Because the disk here is this big, the disk here is that big, and then the one here is that big. All right? So they're going to have different shapes, different sizes. All right. So
is a two-dimensional area. Taking the integral of an area function will give us volume. For example, take this sphere. We can think of this as a series of circular disks of varying radii. If we place the center of the sphere at the origin and we run the disks through the shape horizontally, then we can take the radius of each circle as having the value of y, because it will extend y units from the
x-axis. So that's the radius. How do we find the area of the circle?
We know that the formula for the area of a circle is pi r squared, and we just said that the radius is equal to y. So that's pi y squared. But we want this in terms of the radius of the sphere, because that is unchanging. Let's make a triangle like this, where the distance from the center of the sphere to the center of this
I'm going to move on a little bit.
Many two-dimensional cross-sections, just like the way it gives us a two-dimensional area by adding up infinitely many one-dimensional lengths. But what are these three-dimensional objects, and how can we represent them on the coordinate plane? Well, oftentimes,
so here we go.
shapes will be produced by taking some function and rotating it in a third spatial dimension around the x-axis.
So you're going to be given a function like this. From this, you're going to be able to generate a three-dimensional figure of which you need to find the volume. Okay? So now, suppose there was a disk underneath here like this. This is the radius of that disk. How big is the radius of that disk? It's y, which is equal to, what's y in this case? Root x. Okay? All right? Okay. So,
take something like root x from 0 to 1. Let's fill in this area between the curve and the x-axis.
Okay, watch this. Don't miss it.
Now imagine grabbing this little piece with your hand and rotating it 360 degrees around the x-axis so that it never leaves.
Do you see what happens?
And we see
that's what you need to find the volume of.
In doing so, this is called a solid of revolution because we obtain it by revolving a region about a line. How can we get the volume of this shape? Well, as we said, we just add up all the cross sections by integration. So what is the formula for the area of one of these circular cross sections? Well, the radius is root x because that's how far it is from the x-axis to the function. So pi r squared gives us pi x.
Okay, should we go over that a little bit?
That means that this is what we have to integrate. And luckily, it's as easy as it gets. We pull the pi out front, and x becomes x.
Okay. So look, if I were to draw a disk, so imagine this is the disk, right? At the surface of it. The radius of it goes from the x-axis up. So the radius is the y value, which is the square root of x. So the area of that disk, the outermost disk, is pi r squared pi root x squared. Now, but there isn't one disk only. There are an infinite number of disks. So I have another disk, let's say, here. This disk right here. What's the radius of that disk? From the x-axis up, how much is that? Root x. So the radius is root x. The area is pi r squared, right? And now if I draw 1,000,000 of these and I find the volumes and I add them up, how do I add them up? Using an integral from 0 to 1. That's how I find my volume.
Squared over 2. Evaluating at 1 gives us pi over 2. And since the lower limit is 0, changed about the way we integrate. In fact, when Newton and Leibniz were discovering calculus, there was no one around to hand them integrands because no one even knew what an integrand was. It was questions like the ones that we are considering now that led them to discover calculus.
It's actually
so the fact that we are now finding our own integrands shouldn't come as a total surprise. Unfortunately, this technique does get a little trickier. While rotating one function around an axis gives us one type of solid, if we take the area enclosed between two functions...
Look at this. Now you have two functions, and you want to find this, right? So I'll tell you what, how about we leave that for later, and let's go to our notes. Yes.
So because I'm talking about the example in the notes, it's just because it has two lines and you're finding the volume of what's in between the two lines, you would still do the upper minus lower.
What we just talked about was the fact that you could use these discs drawn inside the figure, and if you add up all of the volumes, then you could find the volume of the big shape. Well, how are we adding up all the volumes, right? If when we drew circular discs, we had to find the area of that disc and then multiply it by the thickness. So basically what we're doing is we're finding the area, multiplying it by dx, right? Area times another dimension, that gives us volume. And we go from A to B, and that gives us the entire volume of the shape, okay? Now, those discs that we talked about, right? So here, right, those discs that we talked about. So basically, if you look at this surface, that circular surface, right, that's called a cross section. You guys know what a cross section is? If you take any old three-dimensional shape, like that cylinder, okay? Now, if I take a knife to it, and if I cut that cylinder right there, okay? And now if I split it open, and if I looked at head-on the surface that the knife sliced through, what shape is that in this case? It's a circle. We call that surface a cross section, right? They do it with trees all the time. How do you know how old a tree is? If you cut it down and if you look at where you cut head on, right, you see the rings, that's a cross section. All right. Now, if I were to take a shape like this, right, and cut it like this, what would be the cross section there? It would be a rectangle or a square or whatever, right? Okay, so in the shapes that we drew, right, that surface is called the cross section, and when you find the area of the cross section, you add up all the areas and then you find the volume, okay? All right, so to find volume, and because we're sort of like we're using cross sections, we call that the method of slicing. So what you want to do is you want to figure out first, what shape does your cross section have? All right? Then based on that, you have to find a formula for AX. So this is the area of the cross section. Okay, now if the cross section is perpendicular to the x-axis, like here for example, this is the cross section, it's perpendicular to the x-axis, right? Like the x-axis like just cuts it. Then we have to do upper curve minus lower curve. If the cross section is perpendicular to the y-axis, so if the cross section looks like this, perpendicular to the y-axis, then we have to do right curve minus left curve. You put in the limits of integration and then you integrate to find the volume. All right, so let's do this first one. Okay, here is my shape, and so I can only this is the two-dimensional one. But imagine if I take, like the blue, and if I rotate this, then I get the three-dimensional shape, right? Yeah. So basically what we're going to do to this is rotate it this way. Okay? Now, I'm going to ask you to imagine a little bit more. Okay, so now you imagine that we rotated it, right? So now it's like a shell. Okay? Now, imagine if I take this, that's like, standing upright, and if I were to lay it on the floor, it would look like this, right? That shell would look like this. Now, inside of that shape, I don't have to do, inside of that shape, I don't have to do circular cross sections. I can also do square cross sections. I can't draw it very well, but I could also do like square cross sections inside. All right, so we're going to start with a square first. All right, so imagine, look at what this says. A solid lies between the planes perpendicular to the x-axis from x equals 0 to x equals 4, from 0 to 4. The cross sections, which are squares with bases in the xy plane, okay, so that's what we need to focus on. The cross sections are squares, and that's what it looks like, are perpendicular to the x-axis between y equals negative x to y equals root x. So look, this is y equals root x, y equals negative root x. Where is that here? Y equals root x, y equals negative root x. Okay? Find the formula for the area of one cross section and use it to find the volume of the solid. Okay? So, cross section is what shape? Square. What's the formula for the area of a square? It's x squared or s squared, right? Okay. This is a picture of the cross section. How big is a side? So how big is it from here to here? Root x. Right? This is root x. How many of those are in one side of this? 2. 2. So how much is the side here? 2 root x. So then the area of the cross section is 2 root x squared. Right? So what's the area of the cross section? It's 4x. Do you see how we did that? I forgot about everything else I know. I just focused on a square. Focus on things you know. A square, I know a square. I know how to find the area of a square. It's the side squared. So now I'm like, okay, how much is the side? Well, since I'm doing calculus, I know that from the axis to the edge of the curve is the y value. And, you know, that's half the size of the square times 2. Okay, so now how much is the volume of this going to be? Volume, what we're going to do is we're going to integrate a of x dx from a to b. So we're going to integrate. The area is 4x dx from a to b. So on the x-axis, where does this start and where does it end? 0 to 4. Okay, so if we do this by hand, because we missed doing this by hand, this is going to be 2x squared from 0 to 2. 2 times 2 squared minus 0. How much is that? Oh, 0 to 4 or 2? 4. So 16 times 2, 32. All right, questions? Yes, no? Okay. Now, somebody made these. Remember how when we were looking for area, we could have drawn rectangles or we could have drawn trapezoids? Okay, so here, inside the shape, you could draw a series of squares. You could draw a series of circles. You could even draw right triangles, okay? You could draw semicircles. You could draw equilateral triangles. Let's do one, the same one actually, but this time what we're going to do is we're going to draw cross sections that are semicircles. So let's draw what we have there. What we have there was this root x and negative root x, and we went from 0 to 4. Okay, cross sections that are semicircles with diameters in the xy plane. Okay, Can everybody imagine what that looks like? A diameter in the XY plane. First thing I do is I draw whatever is on the plane of the shape. So here it says diameters in the XY plane. I'm going to draw a diameter. Here is my diameter. Okay? Now, over here, what is this supposed to be? This is supposed to be a semicircle, right? So look at what I do. I draw a semicircle, and then the part of the shape that's lying inside my figure, I sort of color coded. And so now you see how it's color coded? So if you take this, right, in 3D, and then if you hold it over like that, then that's the shape that we're looking at. Okay? So now what I need to do is I need to find the area of a semicircle. And I know what that is, right? It's half pi r squared. Is that right? So now, how much is r? This is r, but in my calculus problem, r is what? Y, or root x, right? So the area of my semicircle is equal to half pi root x squared. So now a of x is equal to half pi x. All right? So again, first just zero in on that shape. Square, semicircle, triangle, whatever. We know how to find the areas of those from geometry. Figure out how much that length is, and then, just go from there. So now the volume is going to go from 0 to 4 of half pi x dx. Okay? How much is the volume of that going to be? So this is x squared over 2, so it's pi x squared from 0 to 4. How much? 16 pi. The 1/2? Oh, wait a minute. It's over 4. It's over 4. So 4 pi. Okay? All right, let's do another one. We're going to do another one. This time, a solid lies between planes perpendicular to the x-axis from x equals -2 to x equals 2. The cross sections, which are isosceles right triangles, so now the cross sections are isosceles right triangles with bases in the xy plane, are perpendicular to the x-axis. And they run from y equals 4 minus x squared to 0. What does that equation for the square root of 4 minus x? It's a semicircle. And okay, so this figure is going from -2 to 2, and it's a semicircle. So here y is equal to the square root of 4 minus x squared. Okay? The shapes inside are isosceles right triangles. Okay? So what's an isosceles triangle look like? Right. Isosceles right triangle, right? This is the base, this is the height or whatever, and then the base is going to be here inside. Yes. The cross sections here are isosceles right triangles. Yes.
Isn't that kind of just approximating because there's a little contact over when you're taking isosceles triangle out? Because I saw the triangle one circle.
Right, and neither were the squares. That's why some will give you a better estimate than others. Just like I was answering Dylan's question, when we did Riemann sums, the LRAM or the MRAM or the RRAM, based on how much they left out, gave us different approximations.
Is there like any way to calculate like the actual volume?
There is. So it turns out the circles are the best, the circular cross sections. All right. So the cross section, right, are isosceles right triangles. So you see here, this is the isosceles right triangle with that base as the side there that's perpendicular to the x-axis. All right. So now, how much, okay, so now we need to find the area of this, right? The area is half times base times height. How much is this? Which is the same as this distance. How much is that? Root 4 minus x squared. So how much is that? Root 4 minus x squared. So then this is half of squared. Root 4 minus x squared times root 4 minus x squared, so squared. So this is half of 4 minus x squared. So that's the area. Woohoo! Now what are we going to do? We need to find the volume, which is the integral of half 4 minus x squared dx, and it goes from what to what? Negative 2 to 2. And I am going to have everybody plug this in their calculator, and everybody is going to get 5.333. So circular cross sections do give us the best of these approximations, right? Because you could see here, there isn't going to be much that's going to be left out, right? If you just have like a series of circles. So, like we saw in the video, you know, we are going to use something like this to generate, let's say, a solid of revolution. And so if I have this disk here, right, what's the area of that disk? It's a circular disk, so what's the area of it? Area of the circle is pi r squared. But r is always what? Y or f of x. So area is also pi f of x squared, right? And so if we're always using circles and it's always going to be pi r squared, it's always going to be pi f of x squared. So you know what? We could almost like make it into like an automated like mechanism, and we could always just say the area is always going to be pi f of x squared. Okay? And so you just sort of, you know, you plug that in. Sure. And then the volume, I'm trying to get the volume here. The volume is going to be from A to B, pi, this is the region, f of x squared, right? So we're always going to just say volume is from A to B, pi, f of x squared, but we always, dx, but we always put the pi outside. So it's pi A to B, f of x squared dx. So what do you think the most common mistake is here? Well, you can put the pi wherever, but it does have to do with the pi. What do you think the most common mistake is with forgetting the pi to begin with? Okay, now this is okay. So just like you forget the, you know, the plus c, the plus c, the plus c. Technically, if you forget the plus c, you don't get a like that. The number value that you get is still correct, right? But if you forget the pi, then there's nothing correct. Okay. Because these disks are circles, and the area of each circle is pi r squared. So it's always pi times this r squared. Pi f of x squared. Pi day is next Thursday. Okay.
Oh, we don't have
Class next Thursday. Wow, that sucks.
We do on Friday.
Okay. Friday is pi plus 0.01 day, and that's not as fun.
You can bring it.
The region between the graph of f of x equals 2 plus x cosine x and the x-axis, Eli, so here we go. Now we have f of x and the x-axis, okay? This is an important point. Listen, it's an important point because you have to know where your region starts and where your region ends. So your region is going to start there and end right there, okay? And now that is being rotated across the x-axis. From the interval -2 to 2, it's being revolved this way around the x-axis, all right? So, and when you revolve it, this is the shape that you get. Isn't that a cute little shape? It's like a vase, I know. Okay, so we need to find the volume using a calculator. Okay, so the area, right, is pi r squared, but you know that r is just f of x, right? So the area is pi, and then 2 plus x cosine x is the function squared. The volume then is the area squared. So it's going to be pi 2 plus x cosine x squared from -2 to 2. What did I forget? Dx. Okay? Go ahead and plug it in your calculators and tell me the answer to 3 decimal places. You know what? Don't tell me just yet. Hold on to it. I'm going to walk around and look at your answers to this. So this is 52.429. Now, what I'm going to do is give you, I'm going to stop teaching here. I'm going to give you this one.
Is this practice or homework?
Homework. Okay, I'm going to give you this handout for homework. I want you to do the first page only, right? Not very long. So it's like direct practice of what we did here, all right?